Welcome! In this session, we will dive into problem number 857, titled Minimum Cost to Hire K Workers. We'll explore the problem statement, examine different approaches, and break it down step by step. Let's get started. In this problem, we are tasked with hiring exactly K workers from a pool of N workers, where each worker has two key attributes, a quality value and a minimum wage expectation. The challenge lies in the fact that when hiring a group of workers, the wages we pay must adhere to specific rules. First, all workers in the group must be paid in a consistent ratio of their quality to their minimum wage. This ensures that the relative payment respects each worker's individual wage demand. Second, the wages for all workers in the group are calculated based on the highest quality-to-wage ratio among the selected workers. This means that if one worker has a higher ratio, their ratio determines the payment for everyone in the group. Our goal is to find the minimum possible total cost to hire exactly K workers while satisfying these constraints. The problem guarantees that answers within a tolerance of 10 to the power of -5 from the actual value are considered acceptable. The input for the problem consists of three components. First, we have an integer array quality, where each element represents the quality of a worker. Second, there is an integer array wage, where each element corresponds to the minimum wage expectation of the respective worker. Lastly, we are given an integer k, which specifies the exact number of workers we need to hire. The output is a single floating point number that represents the minimum cost required to hire exactly K workers. To better understand this, consider the first example. Here, the quality array is 10, 20, 5, the wage array is 70, 50, 30, and K is 2. The solution involves hiring workers 0 and 2. Worker 0 has a quality-to-wage ratio of 7, while worker 2 has a ratio of 6. Since we must choose the higher ratio of 7, worker 0 is paid 70, and worker 2 is paid 35, resulting in a total cost of 105. This total cost of 105 is the minimum cost required to hire exactly 2 workers in the first example. Now, let's look at the second example. Here, the quality array is 3, 1, 10, 10, 1, the wage array is 4, 8, 2, 2, 7, and K is 3. The optimal solution involves selecting workers 2, 3, and 4. Their respective quality-to-wage ratios are 0.2, 0.2, and 7. Again, we must use the highest ratio, which is 7, to calculate payments. Worker 2 is paid 7 times their quality of 10, resulting in 70. Worker 3 is also paid 70, and worker 4 is paid 7. The total cost is then calculated as the sum of these payments, which is 30.67 when rounded to 5 decimal places. This is the minimum cost to hire exactly 3 workers while satisfying the problem's constraints. To solve the problem, one approach we could consider is a brute force method. The intuition here is to explore all possible combinations of K workers and calculate the total cost for each combination. This ensures we find the minimum cost, as we're checking every viable group. Now, to satisfy the wage requirements, the ratio of wage to quality must be consistent across all workers in the group. The cost for any group is determined by the worker with the highest wage to quality ratio, as their wage dictates the proportional pay for everyone else. However, the complexity of this approach becomes a major limitation. Generating all combinations of K workers from a pool of N workers has a worst-case complexity of n to the power of K, making it impractical for larger inputs. While straightforward to implement, this method is computationally expensive and not suitable for solving the problem efficiently when N is large. A more efficient approach involves using a greedy strategy combined with sorting. The key intuition here is that workers with lower wage-to-quality ratios should be prioritized, as they are effectively cheaper relative to their quality. By sorting all workers based on this ratio, we can ensure that we always consider the most cost-effective workers first. The process works as follows. First, we sort the workers by their wage-to-quality ratio in ascending order. Then, we use a sliding window or a max heap to maintain the K workers with the smallest total quality. The cost of the group is calculated by multiplying the current ratio of the worker being considered with the total quality of the group. As we iterate through the sorted list, we update the total quality and recalculate the cost while keeping the heap size limited to K workers. This approach is more efficient, as sorting the workers takes O n log n, and maintaining the heap of size k requires O n log k. Together, this results in an overall complexity of O n log n. It strikes a balance between efficiency and correctness but requires understanding how heaps and sorting work in practice. The optimized strategy we chose builds upon the greedy approach but incorporates a max heap for better efficiency. Let's break this down step by step. First, the key observation is that the wage-to-quality ratio for each worker must remain consistent within a group. This ensures that all workers are paid proportionally to their quality. To minimize the cost, we aim to minimize the total quality of the group while adhering to these proportional wage ratios. By sorting workers by their wage-to-quality ratio, we can guarantee that we never violate this proportionality constraint. Next, we use a max heap to efficiently track the K workers with the smallest total quality. The process involves iterating over the sorted workers, adding each worker to the heap. If the heap size exceeds K, we remove the worker with the largest quality, ensuring the total quality remains as low as possible. For each valid group of K workers, we calculate the cost as the total quality multiplied by the current workers ratio and update the minimum cost if needed. This approach works because sorting by ratio ensures correctness, and the heap helps us maintain efficiency. The sorting step has a complexity of O n log n, while heap operations contribute O n log k, resulting in a total complexity of O n log n. When comparing the different approaches, it becomes clear why the greedy strategy with a heap is the best choice. The brute force method, while simple in concept, has a prohibitive complexity of O n to the power of k, making it unsuitable for large inputs. On the other hand, the greedy approach with sorting is far more efficient, with a complexity of O n log n. It takes advantage of the problem structure by sorting workers and using a heap to minimize total quality dynamically. By leveraging these insights, the greedy method achieves optimal cost efficiently. Ultimately, the ability to sort workers by their wage-to-quality ratio and use a heap to maintain the smallest total quality ensures that we solve the problem effectively even for larger datasets, making it the clear winner among the approaches. In this problem, we aim to hire exactly K workers while minimizing the total wage cost. Each worker has a quality score and a minimum wage expectation. A key fairness constraint is that all workers in the selected group must be paid proportional wages based on their quality scores, which means the ratio of wage to quality must remain the same for all selected workers. To solve this, the first step is to sort workers by their wage to quality ratio. This ensures that we can evaluate potential groups in the order of their fairness constraint. To do this, we create a list of tuples where each tuple contains the wage to quality ratio and the quality for a worker. Then, we sort this list by the wage to quality ratio in ascending order. Once sorted, we move on to efficiently calculate the cost for groups of workers using a sliding window approach. By maintaining a sliding window of K workers, we can track and update the group while ensuring that the total quality remains optimal. To achieve this, we use a max heap to manage the worker's quality, removing the worker with the highest quality if the window exceeds size K. This helps us keep the group size manageable and focused on minimizing the total cost. Next, we calculate the total cost for each group of K workers in the sliding window. The key here is that the total cost of hiring a group is determined by the worker with the highest wage to quality ratio in the group, which we'll call R. The total cost for the group is simply R multiplied by the sum of the qualities of all workers in the group. To do this efficiently, we keep track of the current sum of qualities within the max heap. Whenever the heap contains exactly K workers, we compute the total cost as R multiplied by the sum of qualities and compare it to the current minimum cost. If it's smaller, we update the minimum cost. Sorting by wage to quality ratio ensures that the fairness constraint is always maintained, and using a max heap allows us to efficiently manage the group of workers. Additionally, once we start calculating costs for groups of size K, we avoid unnecessary calculations for invalid groups, which keeps the algorithm efficient. The use of these data structures, heap for quality management and a sorted list for fairness, ensures that the algorithm remains both correct and optimized. The complexity of this algorithm comes from two main components. First, sorting the workers by their wage to quality ratio takes O n asterisk log n, where n is the total number of workers. This is the most time-consuming step. Second, heap operations, which involve adding and removing workers, take O log k per operation. Since each worker is added and removed from the heap at most once, the total heap operation cost is O n asterisk log k. Combining these, the overall time complexity of the algorithm is O n asterisk log n, as the sorting step dominates when n is large. For edge cases, if k equals 1, the solution is straightforward: select the worker with the smallest wage-to-quality ratio. If all workers have the same quality, the algorithm still works correctly because sorting by ratio ensures proper group selection. Finally, if there are fewer than k workers available, the algorithm should handle this gracefully, either by returning an error or a specified failure condition, as no valid group can be formed. Let's walk through an example to see the algorithm in action. Suppose we have 3 workers with qualities 10, 20, 5, and wages 70, 50, 30, and we need to hire k equals 2 workers. First, we compute the wage-to-quality ratios for each worker. The results are 7.0, 10, 2.5, 20, 6.0, 5. Next, we sort these ratios, resulting in 2.5, 20, 6.0, 5, 7.0, 10. Now, we use a sliding window to evaluate groups of workers. Initially, we add the worker with a ratio of 2.5 to the heap. The heap now contains 20, and the total quality sum is 20. Next, we add the worker with a ratio of 6.0. The heap becomes 25, and the quality sum is 25. We calculate the cost for this group as 6.0 multiplied by 25, which equals 150. Then, we add the worker with a ratio of 7.0, but since the heap now exceeds k, we remove the worker with the highest quality 20. The heap becomes 10, 5, and the quality sum is 15. We calculate the cost for this group as 7.0 multiplied by 15, which equals 105. The minimum cost across all valid groups is 105, so that becomes the final result. To summarize, this algorithm effectively balances the fairness constraints and cost minimization requirements of the problem by leveraging sorting and heap-based optimization techniques. Sorting ensures that the fairness constraint is always satisfied, while the max heap allows us to efficiently manage the group of k workers to minimize the total cost. The combination of these techniques ensures that the algorithm is both efficient and scalable, even for larger inputs. By focusing on the wage-to-quality ratio and dynamically maintaining the group's quality sum, we achieve an optimal solution that adheres to the problem's constraints. The problem requires finding the minimum cost to hire exactly k workers while adhering to fairness constraints. Here's the reasoning behind the solution. 1. Input data preparation. The workers are represented by 2 lists: quality, workers' efficiency, and wage, minimum expected wages. The goal is to hire k workers such that their total wage is minimized while maintaining proportionality. 2. Sorting by wage-to-quality ratio. Workers are sorted by their wage-to-quality ratio in ascending order. This ensures that we prioritize fairness by selecting workers with the least cost per unit of quality. 3. Max heap for quality management. A max heap is used to track the largest qualities among the selected workers. Since Python's heap implements a min heap by default, qualities are stored as negative values to simulate a max heap. The total_quality variable keeps track of the sum of the selected workers' qualities. 4. Iterating through workers. For each worker in the sorted list, add their quality to the heap and update the total quality. If the heap exceeds k workers, remove the worker with the highest quality, lowest negative value in the heap, to ensure only k workers are considered. If exactly k workers are in the heap, calculate the total wage cost as total_quality** ratio, where ratio is the current worker's wage-to-quality ratio. Update the min_cost with the lower of the previous and current costs. 5. Result. The algorithm returns the minimum cost computed after iterating through all workers. This approach efficiently calculates the minimum cost due to sorting, O n log n, and heap operations, O n log k. The solution is optimized for scenarios where n, number of workers, can be large, as it avoids brute force combinations. Here, we start by importing the necessary Java utilities and defining our solution class. The method minCost_to_hire workers takes in an array of quality, an array of wage, and an integer k representing the number of workers we need to hire. First, we combine the quality and wage of each worker into a single list of worker objects. Each worker stores their quality and the ratio of their wage to quality, which we calculate by dividing the wage by the quality. This ratio is critical because it represents the minimum payment per unit of quality required by each worker. After creating this list, we sort the workers based on their ratio in ascending order. This ensures that we consider the most cost-efficient workers first. Next, we set up a max heap using a priority queue to keep track of the largest quality values among the workers we've selected so far. We also initialize a variable total quality to store the sum of the selected workers' qualities and set min cost to a very large value to track the minimum cost as we iterate through the workers. For each worker in our sorted list, we add their quality to the heap and update the total quality. If the size of the heap exceeds k, meaning we have more than k workers, we remove the worker with the largest quality from the heap. This is because including them would result in a higher cost, and we only need k workers. Now, once we have exactly k workers in the heap, we calculate the cost of hiring them. The cost is determined by multiplying the total quality of the selected workers by the current workers ratio, since the highest ratio among the selected workers dictates the payment for all of them. We then compare this cost with the min cost we've been tracking and update it if the current cost is lower. After iterating through all workers, we return the minimum cost found as the result. Finally, we define a helper class called worker to store each worker's quality and their wage to quality ratio. This class simplifies the process of managing and sorting the workers. By structuring the problem in this way, we efficiently calculate the minimum cost to hire exactly k workers while ensuring that each worker's payment meets their respective wage expectations. To solve the problem, we start with the given input: quality equals 10, 20, 5, wage equals 70, 50, 30, and k equals 2. The first step is to pre-process the data. We pair each worker's quality and wage into tuples, resulting in 10, 70, 20, 50, 5, 30. Next, we sort these workers by their wage to quality ratio, which helps us prioritize workers who are more cost efficient. After sorting, the workers are ordered as follows: 5, 30 ratio equals 6.0, 20, 50 ratio equals 2.5, 10, 70 ratio equals 7.0. This ensures that the most affordable workers are processed first. Now, we initialize our variables. We set up a max heap to store the negative of worker qualities, making it easier to remove the highest quality later. The total_quality variable tracks the sum of qualities in the heap, and we initialize min_cost to infinity as we aim to find the minimum cost. In the first iteration, we process the worker 5, 30. Their quality is added to the heap as -5, and the total_quality becomes 5. Since the heap size is less than k, we don't calculate the cost yet and move on. Now, we process the next worker, 20, 50, in the sorted list. Their quality, -20, is added to the heap, resulting in heap equals -20 minus 5. The total_quality is updated to 25. Since the heap now contains exactly k workers, we calculate the cost. The ratio for this worker is 50/20 equals 2.5, and the total cost is total_quality asterisk ratio is equal to 25 times 2.5 equals 62.5. We update min_cost to 62.5 as this is the lowest cost so far. Moving to the third worker, 10, 70, we add their quality, -10, to the heap, giving heap equals -20 minus 5 minus 10. The total_quality becomes 35. Since we only need k workers, we remove the worker with the highest quality, which is -20. The heap becomes -10 minus 5, and the total_quality is updated back to 15. We then calculate the cost for this worker. With a ratio of 70/10 equals 7.0, the total cost is 15*7.0 equals 105. However, this cost is higher than the current min_cost of 62.5, so we don't update it. At the end of this process, the minimum cost for hiring 2 workers is 62.5. The final output for this example is 62.5. Let's now work through another example to understand the solution further. Here, we have quality equals 4, 8, 6, 2, wage equals 60, 100, 90, 30, and k equals 3. We start by pairing the quality and wage values into tuples 4, 60, 8, 100, 6, 90, 2, 30. Sorting by the wage to quality ratio results in 2, 30-15.0, 4, 60-15.0, 6, 90-15.0, 8, 100-12.5. This ensures the workers with the most cost-efficient ratios are considered first. We initialize the variables, an empty max heap for qualities, total_quality equals 0, and min_cost equals INF. Processing the first worker, 2, 30, we add their quality, -2, to the heap. The total_quality becomes 2. Since the heap size is less than k, we skip the cost calculation for now. Next, we process worker, 4, 60. Adding their quality, -4, to the heap results in heap equals, -4, -2, and the total_quality is updated to 6. Again, since the heap size is still less than k, we don't calculate the cost. Moving to worker, 6, 90, we add their quality, -6, to the heap, giving heap equals, -6, -2, -4. The total_quality becomes 12, and now that the heap contains exactly k workers, we calculate the cost. The ratio for this worker is 15.0, and the total cost is 12*15.0 equals 180. We update the min_cost to 180. Lastly, we process worker, 8, 100. Adding their quality, -8, to the heap gives heap equals, -8, -6, -4, -2. The total_quality becomes 20, but we remove the worker with the highest quality, -8, reducing the heap to, -6, -4, -2, and updating total_quality to 12. We calculate the cost using this worker's ratio of 12.5, resulting in 12*12.5 equals 150. This is lower than the previous min_cost, so we update it to 150. The final output for this example is 150. This demonstrates how the algorithm efficiently minimizes the total cost to hire k workers by maintaining a max heap for qualities and iterating through workers sorted by their cost effectiveness. By continuously updating the min_cost as we process each worker, we ensure the solution is optimal. This strategy balances the trade-off between hiring cost and total quality, resulting in the minimum possible cost for the given constraints. To analyze the time complexity of the algorithm, we start by looking at the major components contributing to it. First, we have the sorting step, where the workers are sorted based on their wage-to-quality ratio. Sorting requires n*log n time, where n is the number of workers. Next, we iterate through the sorted list of workers, which is a single pass and takes n time. During this iteration, we perform heap operations. Specifically, we add each worker's quality to a max heap, which has a time complexity of log k per operation, where k is the maximum size of the heap. Additionally, if the heap size exceeds k, we remove the largest quality, which also takes log k time. Since these heap operations could occur for each of the n workers, the total heap-related complexity becomes n*log k. Together, these steps outline the key contributors to the overall time complexity. Now, combining the steps, we see that sorting the workers takes n*log n, while the iteration and heap operations contribute n*log k. Between these, the sorting step dominates when n is large because log n grows faster than log k. Therefore, the overall time complexity of the algorithm is n*log n. Shifting our focus to space complexity, the algorithm uses n plus k space in total. This comes from three main components. First, the workers list requires n space to store the quality and wage data for all workers. Second, the max heap can hold up to k worker qualities at any given time, contributing k space. Finally, the auxiliary variables such as total_quality and min_cost use constant space, 1. When combined, these factors result in a total space complexity of n plus k. The space complexity of n plus k provides an efficient use of memory for this problem. To better understand the advantages of this optimized approach, let's compare it to a naive solution. A straightforward but inefficient method would involve generating all possible subsets of k workers from the n available workers. This requires evaluating n choose k combinations. For each subset, calculating the total cost involves summing the qualities and computing the wage-to-quality ratio, which takes k time per subset. As a result, the time complexity of the naive approach becomes n choose k*k, which is exponential and computationally infeasible for large values of n. In contrast, the optimized approach leverages sorting and maintains a max heap, reducing the problem to n*log n time. This makes it far more scalable and practical for real-world applications. When we analyze the algorithm's performance across different cases, the time complexity consistently remains n*log n. In the best case, the sorting and heap operations dominate regardless of the input, leading to n*log n complexity. Similarly, in the average case, the algorithm must still sort the workers and process each one in a loop, resulting in the same complexity. Even in the worst case, where the number of workers and the heap size are maximized, the upper bound remains n*log n. This consistent performance across all scenarios highlights the efficiency and robustness of the algorithm, making it well suited for solving the problem of hiring workers at minimum cost. When solving this problem, there are several common mistakes to watch out for. First, failing to handle edge cases can lead to incorrect results. For example, if k is equal to 1, or if k equals the total number of workers, the solution may behave unexpectedly unless these scenarios are explicitly considered. Testing with both minimal and maximal values of k is crucial. Another issue is ignoring numerical stability. Since the problem involves ratios and divisions, rounding errors or floating point inaccuracies can affect comparisons. To avoid this, use precise arithmetic or sort values to maintain consistency. Inefficient subset generation is another pitfall. If you generate all possible subsets of workers, especially for large inputs, it can make the algorithm computationally expensive. Instead, optimized approaches like sorting or using a greedy algorithm are much more efficient. Additionally, overlooking problem constraints, such as the maximum value of n being up to 10 to the power of 4, can result in time limit exceeded errors. It's important to always design your solution with the worst-case complexity in mind. Finally, be cautious when using priority queues. Forgetting to maintain the correct heap property, such as distinguishing between a min heap and a max heap, or improperly handling pops from the heap can lead to incorrect results. Paying attention to these details will help ensure your solution is both correct and efficient. Now, let's consider some insights that are particularly useful in an interview setting. Understanding the difference between greedy and brute force approaches is key. It's often not enough to just code the solution, you should be able to explain why a greedy approach works or why it doesn't in a given scenario. This demonstrates your problem-solving ability. Optimizing early is another valuable strategy. If a brute force solution is too slow, think about how you can reduce complexity. For instance, sorting the input or using efficient data structures like heaps can make a big difference. It's also important to communicate trade-offs effectively. For example, while a priority queue might reduce time complexity, it could increase space usage, so being able to discuss these trade-offs shows a deep understanding of your approach. Testing thoughtfully is another critical skill. Make sure to test your solution with edge cases and stress test it with large inputs. During an interview, walking through the algorithm with small examples can help you demonstrate clarity and confidence. Additionally, exploring related problems is a great way to deepen your understanding. Problems like find k-pairs with smallest sums or find median from datastream share similar techniques and can provide further practice. Finally, let's explore some alternative approaches that can be used to solve this problem. One effective method is sorting combined with a sliding window. By sorting workers based on their quality-to-wage ratio, you can efficiently track the k-workers with the smallest quality sum using a sliding window. This approach avoids the inefficiency of generating subsets and has a complexity of n log n due to the sorting step. Another common strategy is to use a priority queue, or max heap, to maintain the k-workers with the smallest quality as you iterate through the sorted ratios. This allows for efficient updates and ensures that the cost calculation remains optimal at each step. While this approach requires additional space for the heap, it significantly reduces the time complexity for managing the k-workers. In some variations of the problem, dynamic programming can also be applied to track the minimum cost for subsets of workers. However, this approach is generally less efficient for large inputs due to higher time and space complexity compared to greedy methods. Each of these approaches has its own trade-offs, and the best choice often depends on the specific constraints and requirements of the problem at hand. Great job! We've covered the key aspects of the problem and discussed its optimal solution. Remember to practice problems like this to strengthen your understanding of sorting, priority queues, and greedy algorithms. Thanks for tuning in. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!